fundamental theorem of algebra. The fundamental theorem of algebra states that a polynomial function of degree n greater than 0 has n complex zeros. Some of these zeros may be repeated. So basically what this is telling you is f of x equals x to the fourth minus 3x squared minus 2 has 4 complex zeros. And I got the 4 from the lead coefficient. On the second one, f of x equals x to the 7th minus x to the 3rd minus x plus 2 would have 7 complex zeros. And that was derived from the lead coefficient of 7. The linear factorization theorem. If f of x is a polynomial function of degree n greater than 0, then f of x has precisely n linear factors. And f of x equals a times x minus z sub 1 times x minus z sub 2 times x minus z sub n. All this is where a is the leading coefficient of f of x, and z sub 1 times z sub 2 z sub m are the complex zeros of f of x. The z sub I are not necessarily distinct numbers, and some must be repeated. This is a theorem that will come into play later on. Writing polynomial functions in standard form and identifying the zeros of a function. If you notice, this looks familiar, but it's slightly different because we have the imaginary number in there. If I were to ask you what the zeros of this function are, I would hope you would be able to tell me that for this first factor, it would be 2i, and for the second factor, it would be negative 2i. If I asked you what this function is, we could find it by foiling it, but because one of these has a plus and one of them has a minus, we can take the shortcut method and just go x times x, which gives me x squared. And I'm going to have a minus, and 2i times 2i is going to give me 4i squared. Since I squared is equal to negative 1, I will change that to a plus 4. So my function, f of x, is going to equal x squared plus 4. So that wasn't too bad, trying to find that function with the imaginary zeros. And if I look at the graph of that function, this is what it looks like. And if you notice, right here is where my x-axis is. And if you notice, it doesn't cross the x-axis. Therefore, it does not have any real zeros. They are both imaginary. Zeros or roots. This one is a little bit more daunting in that it's going to be an x to the 4th equation because I have 4 zeros. I have 4 roots here, one being negative 3, one being positive 3, negative I, positive I. And it's not that difficult to find out what this x to the 4th equation is if I choose the right two to multiply together at the right time. If I multiply these first two together, I would get x squared minus 9. If I multiply the second two together, I get x squared minus I squared. That in turn changes to x squared plus 1. Now I can take x squared minus 9 times x squared minus, or x squared plus 1. And that in itself is not too difficult. And I get x to the 4th plus x squared minus 9x squared minus 9. And simplified, my function becomes x to the 4th minus 8x squared minus 9. And if I look at the graph of that, this is what my picture looks like. And if you notice here is my x-axis way up here, and I only have 2 real roots or zeros, and 2 of them were imaginary. Complex conjugate zeros theorem. Suppose that f of x is a polynomial function with real coefficients. If a and b are real numbers with b not equal to 0, and a plus bi is the 0 of f of x, then its complex conjugate a minus bi also is a 0 of f of x. What this is telling me, that if you have an imaginary number as a 0 of a function, its complex conjugate must also be a 0 of that function. So if 3 minus 6i is a 0, 3 plus 6i must also be a 0. If 7 plus 5i is a 0, then 7 minus 5i must also be a 0. Polynomial functions of odd degree. Every polynomial function of odd degree with real coefficients has at least one real root. So if I have a function, say 7x plus 3, it's going to have one real root. If I have 5x cubed minus 9x plus 2, it's going to have at least one real root. If I have 3x to the 5th minus 4x squared plus 8, it's going to have at least one real root. And I'm getting that from these because my exponents on my lead coefficients are all odd. They are all odd functions. Determining the number of complex and real zeros from the graphs of functions. This is an x to the 4th function. I know because it's an x to the 4th function, it's going to have 4 complex zeros because of my exponent of 4. Okay. The possible number of real roots it can have, and they're going to come in pairs. It can either have 4, it can have 2, or it can have 0. If I look at the graph of this, here's my x-axis. It crosses the x-axis twice. So I know that it has 2. The number of imaginary roots it can have is also going to be 4, 2, or 0. But because I looked at the graph of this and I figured out that it had 2 real roots, that means it's going to end up having 2 imaginary. Now, if I want you to go on and figure out from there what the rest of the roots are, you are going to have to do P over Q and list all the possible roots, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 36. You need to find both real roots through synthetic division, and then through the quadratic formula, you will find the two imaginary roots. If I look at this x to the third equation, the possible number of complex roots are 3 because it's in x to the third equation. The possible real roots are 3, 1, or 0. The possible imaginary, because imaginary have to come in pairs, they are only going to, possible imaginary ones are only going to be 2 or 0. If I look at my graph, though, here's my x-axis, which I kind of missed there. But this graph crossed in 3 places. So I know this graph actually has 3 real roots. So you're going to need to go through and find these through a combination of P over Q synthetic division factoring and the quadratic formula. Okay, that's pretty much it. Thank you.